a natural exponential function is a function that fits into this form. Y equals some constant c times e to the t power. This would be an example of an exponential function where c is just some constant. And the base is this mathematical constant e. And e is approximately this. To the first 5 digits, e is this. 2.71828 ... This goes on and on and on. It's an irrational number. Okay. When you use that for your base, then it's called a natural exponential function. The reason why this is so useful is this. If you have an equation like this, then dy dt, the derivative of this, is just equal to c times e to the t power. Okay. The derivative function is the same as the original function. It's very easy to get the derivative, and that's why using this base is so useful. Suppose we generalize this just a little bit more. C times e to the RT. Is this what you're talking about? Okay. And in this case, C and R are constants. They're parameters. Okay. And so this is slightly more general than this. In this case, dy dt would be found just, it would be just slightly more difficult. A dy dt in this case would be found as follows. You would have to take the derivative of this term with respect to t and multiply it times this expression here. So this would be r times c times e to the RT. In fact, we could prove that if you just accept this. Let's just accept this. I'm not going to prove this. It's not too difficult to prove it, but the proof is in the book, and but we'll just take it as given. Then you could go back to this expression right here, and you could let W be equal to RT. We could define W to be RT, in which case we would now have Y equals C times e to the W. Now, it's obvious what dy dw is. What is dy dw? Diana? Yeah, it's just c e to the w. But suppose we want dy dt. Well, then we could just use the chain rule. And we could say, well, dy dt is equal to dy dw times dw dt. And what is dy dw? Well, it's this. So you just substitute in for dy dw c times e to the w power times dw dt. What is dw dt? Anybody? Just r. Because w by definition is RT, so dw dt is just equal to r. So just put in an r here. And let me put the r first. So I'll write RC times E, and what is W? RT. Okay, so that verifies that if you have an expression like this, then dy dt is just found by taking the derivative of the exponent, r, down, and then just multiplying it times what's left. Okay. So in this case, it's dy dt is found very easily. Okay. So let me give you a simple illustration of this. Suppose we have this expression. Y equals 100 times e to the 0.05 t. What would dy dt be? In this case, our c value is 100. Our r value is what? 0.05. So just using the rule, dy dt, what do we do to this thing right here? That exponent? Yeah, okay. You just differentiate with respect to t, you get 0.05. So you bring 0.05 times 100, 0.05 times 100 times e to the 0.05 t. And 0.05 times 100 is obviously just 5. So you get 5 times e to the 0.05 t. Okay, so that would be dy dt. One other thing that's very useful and very convenient, when you have an expression like this, y equals c times e to the rt, the interpretation of that r is just the instantaneous growth rate of y. Okay. R is just the instantaneous growth rate of y. To see that, notice dy dt, that's the derivative of y with respect to t. That is just rc times e to the rt. If you want to convert that into a growth rate, all you have to do is take dy dt and multiply it by 1 over y. Then it's a growth rate. The growth rate of y, let me just write this out. The growth rate of y. Sometimes it's referred to as the instantaneous growth rate as well. The growth rate of y is just this. It's 1 over y times dy dt. This should make intuitive sense because this is the same thing as dy over y over dt. dy over y is just the proportional change in y, or the percentage change in y, over dt, so it's the proportional change in y with respect to time, the growth rate. Okay. Now, here is dy dt. Suppose we multiply this by 1 over y. Then this becomes the growth rate of y. And if you substitute in for y here, y is equal to this, so you get r c e to the rt power divided by c e to the rt. This cancels, and you just get r. So in this equation right here, what is the growth rate of y? Growth rate of y is, 0.05, or 5%. 0.05, or in percentage terms, 5%. So in this equation right here, in this exponential, natural exponential function, y is growing constantly at 5%. The instantaneous growth rate of y is always 5%. Okay. So you could see how these exponential functions are quite useful. Anytime you have a process that's growing at a constant growth rate, it's easy to express it as a natural exponential function.